In this lecture, I'm going to talk about fuzzy clustering and manifold learning. And also afterwards, I'm going to talk a bit about some additional information that you need for the second assignment. For example, comparing your clusters with some external index using the RAND index. And I'm going to also talk a bit about the second assignment. So give a short presentation on what the second assignment is. But first, let's start with fuzzy clustering. The idea here behind fuzzy sets is to try to capture some amount of vagueness or uncertainty in our concepts. So in conventional set theory, we say that elements either belong or don't belong to a set. This is a Boolean thing, all or nothing. In fuzzy set theory, we have a membership function that is a continuous value for each example between 0 and 1 and indicates how much that example, that element belongs to some set. So the membership function of x to set S will give us a quantification of how much x belongs to S. More formally, a fuzzy set is a set of ordered pairs where we have for each example the membership function, the membership value of that example for belonging to a given set. So this allows us to model uncertainty or vagueness in a way that simply belonging or not belonging cannot capture. For example, we have some temperature and we have these categories of cold, warm, and hot. And there is no good frontier that we can specify that really determines the separation between cold and warm, such that the temperature is either cold or warm, or is either warm or hot. Rather, we have some intermediate ranges where a temperature may be a bit warm but rather cold, or mostly warm but a bit cold, or something like that. And fuzzy sets, fuzzy logic allows us to capture this kind of vagueness or uncertainty in the concepts. So one thing to note is that fuzzy membership is not probability. Even though it's also between 0 and 1, it does not need to respect those conditions that probabilities have to respect, such as the sum of the probabilities of different events must add up to 1 and things like that. So we can consider a fuzzy C partition of a set of points. If we have this membership function for each point and for each of the groups of the partitions, that goes from 0 to 1, and this tells us how much each example belongs to each group, to each set, in this case a fuzzy set. If each example the membership over all the different fuzzy sets adds up to 1. So each example is distributed through all the possible fuzzy sets in a way that the membership function totals 1. And also there is the sum of the membership values for all the examples over all the different, for each different set is never more than the number of examples. So this basically tells us that we cannot have more membership, total membership in one set than we have of a total number of examples. So if we respect these conditions, we have a fuzzy C partition with this number of C groups, fuzzy sets in our partition. Now, with this concept, we can see an adaptation of k-means to fuzzy sets with fuzzy C-means. So this, in this case, we have C, which is the number of fuzzy sets to which our examples will belong. We have a set of X, of n unlabeled examples, so we're going to represent this set as X. And now fuzzy C-means will give us the membership matrix, or all the values of the membership function for all the C fuzzy sets and all the n elements we have. So this matrix will tell us how much each example belongs to each of the C sets that we specified. It also returns the centroids of the C sets that we have, so similar to k-means, and it's minimizing this error function. So this is basically the same idea with k-means, where we are minimizing the sum of the squares of the distances between all points that belong to one cluster and the centroid for that cluster. But in this case, the points do not simply belong to a cluster. They have a membership function that is a continuous value. So we are doing this for all points, multiplying the distance to the centroid by the membership function raised to this factor, this falsification factor here, which is usually greater than 1, that basically weights the fuzziness of our clustering. So this has this constraint: we cannot assign more than 1, or we must assign exactly 1 membership in total for each example. So because we want a fuzzy C partition, but what we're doing here is basically similar to k-means, with this adaptation that we are using a continuous membership function, and this degree of fuzzification, this factor here, is typically the one typical value to use is 2. So this is how much the fuzziness is weighing on the clustering. But we can adapt this factor here. So solving this in a way similar to k-means, we get the membership value. So now with k-means, we simply assigned each example to the cluster with the closest centroids. In fuzzy c-means, we are computing the membership value for each example in each of the clusters by looking at this expression of the distance between the example and the centroid of the cluster. So basically this decreases as the distance increases, as a fraction of the same factor computed over all the different clusters. So basically we are assigning a larger membership to the clusters for which the centroids are closer to our example n, and a smaller membership to all the clusters that are farther away. And then we can compute also the optimum value for the centroids based on the membership of all the different examples. And basically this is the equivalent of what we were doing with k-means, which is to compute the mean point of all the examples that belong to the cluster. But in this case, this is a weighted average by using the membership function of each example to the cluster raised to the power of that fuzziness factor there. So this is similar to k-means, only we have this extension with continuous membership. And the result here is this algorithm. So we start, like with k-means, with random centroids. We compute the membership. This is the equivalent of what we were doing in k-means, of assigning points to the closest centroids. Only in this case, we are computing the continuous value of the membership function to each of these clusters. Then we are going to recompute the centroid positions, which again, it's analogous to what we did in k-means. Only in this case, instead of being just the average of the coordinates of all the examples that belong to that cluster, we are doing a weighted average taking into account the membership value of each example for that cluster. So now we repeat this either a fixed number of iterations or until the change is very small. So we consider some threshold under which we assume that we already converged, and we stop the algorithm. So the result of this is a clustering similar to k-means, but we have these membership values. So each point belongs to each cluster with some measure of membership that is a continuous value, and we can get this fuzzy clustering in this way. If we want to convert this into a crisp clustering where each point either belongs or does not belong to a cluster, then we can take something like assign each point to the cluster that has the maximum membership, or the nearest centroid, as if it was k-means, for example. So it's easy to convert from fuzzy clustering into a crisp clustering just by using some heuristic like this. Okay, so now let's move a bit away from clustering and look at manifold learning, which is another type of unsupervised learning, and it is very useful for dimensionality reduction. We already saw one example of this type of transformation with a principal component analysis, but the idea here behind manifold learning is this notion of manifold. So we have, there is a typo here, it should be homeomorphic and not homomorphic. I'll fix this later. But a manifold is a set of points inside a larger dimensional space that in the neighborhood of each point is close to an Euclidean space of lower dimensions. For example, this plot here represents seismic events on the surface of the Earth. So this is represented in 3 dimensions because the Earth is a sphere. So if you represent points on the surface of a sphere, you get something like this in 3 dimensions. But if you look at regions in the neighborhood of each of these points, you can easily transform this into a 2-dimensional map where you place the longitude and latitude of the seismic events. Of course, if you try to represent everything in the map, then there are problems when you reach the edges of the map because you cannot make it go around the entire sphere. But if you look locally in the neighborhood of each seismic event, then you can approximate this very well into a 2-dimensional surface, even though the original data is in 3 dimensions. So this is the manifold that we have in which our data is distributed. So in general, we can consider that the data that we have, even if it's in higher dimensions, is not uniformly distributed over all the possible combinations of features, but rather occupies some subspace of all those possibilities that can be approximated with a lower dimensional representation. For example, in this artificial data, we have the points are in 3 dimensions, but they loop around with this curve. So in theory, if we could find the shape of this curve, we could specify the position of each point along this curve simply by saying how much farther along the curve the point is. So we could reduce this into a single dimension and still have a good representation of the data. So that's the idea of manifold learning. We want to try to find a lower dimensional representation of this data. For example, take this data here and represent it only in 2 dimensions, but in a way that keeps the same kind of topology and the relations between the points. So these are a bit farther away, now these are more close together, and we retain this representation where the neighborhood of each point is still the same kind of distances that we have in the original data. Or we can go farther and reduce this to a single dimension if we manage to go along the curve. Now in this representation, because if I put everything in a single dimension, some points are overlapping, I'm also representing here the points spread out so we can see where they are overlapping. So for example, here we have an overlap of these points. But this would be the reduction to just 1 dimension, and this would be a reduction to 2 dimensions. Okay, so now let's see one way of doing this. T-distributed stochastic neighbor embedding, usually called T-SNE, is a very used method, especially for visualization, for capturing these manifolds in a lower dimension. And the way this works is that in the original space, we have these points, X, that are in some high dimensional space. They can have, say, 10 dimensions, 20, 50, something like that. And now we can measure the probability of or specify a probability of one point I, choosing point J as neighbor, and this is defined in this way. We take these Gaussian distributions using the distance between the 2 points, so the distance in the original space where the points are, and this is basically a Gaussian distribution that is based on the distance between the points. So if the points are close together, the probability is high. If the points start spreading further apart, this goes down with that typical bell shape of the Gaussian distribution. And what we consider to be the probability of J selecting I as a neighbor is this probability distribution based on the distance between the two, divided by the sum of the same calculation, the same kind of distribution, but computed for all for between I and all other points that are not J. So basically, if J is close to I, then is closer to I than all the points, then this will be larger and this sum will be smaller and we have a high probability. Otherwise, we have a lower probability. So this is the measure of probabilities of choosing a neighbor that favors the closest neighbors. It's more probable a point choosing as a neighbor another point that is closer to it than the remaining points. Okay, so from here we can take the average of the probability of J choosing I and I choosing J as neighbors. This gives us an idea of the joint probability of being neighbors. And now we can do the same thing in a lower dimensional representation. So this Y corresponds to the X, but while the X is in the higher dimensional space, for example 20 or 30 dimensions, Y is in a lower dimensional space, typically 2 dimensions, so we can plot in a graph. And now we use this T distribution. This is just because computationally it's simpler to use than the Gaussian distribution, but it's a similar one where we're also considering the same thing. It's more probable that I chooses J as a neighbor if the distance between I and J is smaller, smaller, and the distance to all the others is larger. So this way we have the probability of being chosen as a neighbor in the lower dimensional representation and the probability of being chosen as a neighbor in the higher dimensional representation. Now, the higher dimensional representation, we have the coordinates. This is our data. For the lower dimensional representation, we do not know what the coordinates are because this is the manifold representation we're trying to learn. But what we can do is to change these coordinates or find these coordinates in a way that makes this distribution as close as possible to this one. And so this is one measure of the divergence between distributions. So this is the Kullback-Leibler divergence. But basically what the algorithm, the t-SNE algorithm does is to find the coordinates for the lower dimensional representation that minimize the divergence between these two probability distributions. So basically the probability of being a neighbor of some point in the lower dimensional representation will be as similar as possible to the probability of those points being neighbors in the higher dimensional representation. So this is an example. If we take this initial distribution, we can use t-SNE to reduce this to 2 dimensions, and you see that most points will still retain the same neighbors as they have in 3 dimensions. Of course, there are some gaps here because we cannot really squeeze this into 2 dimensions without losing anything, but other than that, we keep most of the points in the correct neighborhood, and we are creating a representation of these data that captures very well this manifold, these relations between the points. And even when we go down to 1 single dimension here, we can still keep most of the ordering of the points along these lines. So this representation here is just to unravel a bit because some of the points are superimposed, but you see that there are not many superpositions and we keep most of the ordering there. So this is one way of doing this manifold learning and computing a lower dimensional representation that preserves these relations between neighbors. Another example of these algorithms is IsoMap. And IsoMap, the way it works is that it computes the k nearest neighbors for each point. So for example, we can look at the 10 nearest neighbors for each point, and it creates a graph connecting these points. So this is similar to what we did with the connectivity matrix in agglomerative clustering, for example. It's the same idea. So we have a graph that connects each point to its closest neighbors, and we measure the distance between those points that are connected as simply being the Euclidean distance in the original space. So we take the Euclidean distance in our original coordinates. But now we're going to build a matrix with the pairwise distances between all pairs of points, but for points that are not directly connected, so they are not the nearest neighbors of one another, we are not going to measure the distance in the original space. We are going to measure the distance only along this graph. So we're going to look at the neighbors and the neighbors of neighbors and so on until we reach from point A to point B, and we're going to add those distances. So what this does is, if we look at an example like this, what we are doing is basically computing the distance between one point here and another point there, not as being directly over space, but by being measured along the line of this curve. So going through all the nearest neighbors and measuring the distance by adding all these distances here. So this means that the distance matrix that we create here with IsoMap is measured along the manifold and captures how the points are distributed along that manifold. So now that we have these distances, we can compute coordinates that approximately match these distances, so compute this low dimensional embedding, and the result is something like this for this data. So here we have the distances here measured by the nearest neighbors, and this gives us this line that goes here. Then now here the distances start becoming larger, and we have this curve in this way representing this part of the curve. And if we compress this into one single dimension, we can see that the IsoMap algorithm is capturing very well the progression along this curve, even in one single dimension. There are some superpositions here when it reaches the end, but overall it can capture very well the shape of the curve, even when reducing to a single dimension. Now, if we compare capturing this data using manifold learning with this kind of algorithms, if we compare this with PCA, for example, PCA is a simpler way of doing this, but it can only do a linear transformation, and it maximizes the variance. So it cannot actually follow the manifold if the manifold cannot be followed with a linear transformation. If you do PCA in this data set for 2 dimensions, you get something like this. So there's a lot of superposition here. Basically, it found a direction where the variance could be best retained, and then it squeezes everything into 2 dimensions. But with the linear transformation, this is very limited, and if you put this into 1 dimension, then you get a lot of overlap of all the points. So t-SNE and IsoMap are generally better when you need nonlinear transformations. But manifold learning can be done with many different algorithms, for example, self-organizing maps, autoencoders with neural networks, and so on. And in scikit-learn you have several algorithms that you can take a look. The ones that we're going to use for the assignment are these 2, IsoMap and t-SNE. So one thing that you're going to need for the assignment is the ability to compare clusters. So this is where rand index comes into play. Remember this confusion matrix that we had in that we used in supervised learning in classification, where we compared the predictions of our classifier and the actual classes of the examples. So a true positive is when our classifier predicts that it's a positive example and it's actually a positive example. A false negative is when our classifier predicts it's a negative example, but it's false because it's actually a positive example. Then we have the true negative when the class and the prediction both match on the negative, and the false positive when we have a negative example, but our classifier says it's a positive example. So this would be for two classes, the four possibilities. In unsupervised learning, we cannot really match this because we don't have fixed classes. You cannot say that if you run one clustering algorithm, for example, and some points are labeled in cluster 1, and you run another clustering algorithm and it labels those points in cluster 2, you cannot really say this is wrong because the labels for the clusters are arbitrary. They come from the algorithm and they are not in the data. But we can adapt this by considering pairs of points. So instead of just looking at points individually, we consider pairs of points. And we can measure this kind of concept here, true positive, false positive, and so on the pairs of points. So a true positive is a pair that belongs to the same group. So this is some external group. It may be another clustering algorithm, a classifier, something like that. So the points this pair of points come from the same group, and our clustering algorithm placed them in the same cluster. So they should be together, and they are put together by our clustering algorithm. So this is a true positive. A true negative is a pair that should not be together because they are from different groups, and our clustering algorithm placed them in different clusters. So true negative because our clustering algorithm figured out that those 2 points do not belong together. A false positive would be a pair from different groups. It should belong to different clusters, but our algorithm placed them in the same cluster. So our algorithm is saying that they should be together, but in fact they should not be together because they belong to different groups. And then the false negative when they belong to the same group but are placed in different clusters. So this is the idea of the RAND index. We adapt this notion of true positive, false negative, and true negative to pairs of points, and we are measuring whether our clustering algorithm is putting them in the same cluster or in different clusters, and comparing that with the groups where they are. So group here is a deliberately vague term because they can be classes if you have points that were previously classified. They can be other clusters from other clustering algorithm or some other thing. But basically we are measuring the success of our clustering algorithm in the ability to put together things that should be together and keep apart those that should be apart. Okay, so this is basically how you compute the RAND index. For all pairs of examples, and if you have n examples, you have n times n minus 1 divided by 2 pairs, you compute how many are true positive, false negative, and true negative by following these rules, checking if they should be in the same cluster, and if they are in the same cluster, and so on. And using this analogy, we can now compute the analogus of precision, recall, F1 score, and so on, exactly as we did with classification. And RAND index is the analogus of accuracy. So basically, all the possible pairs are here in the denominator, and the sum of the true assignments are here in the numerator. So you add the true positive and the true negative, you divide by the total number, and this will be the RAND index. So this is the equivalent of the accuracy in a classifier. Now, one problem here is that if you have a large number of clusters and a large number of groups, then merely by chance, it's very frequent that points belonging to different groups will be placed in different clusters. So the RAND index can become artificially high just because of the number of clusters that you have. This can be fixed with the adjusted RAND index that takes the RAND index measured and subtracts what would be expected merely by chance. So if you assigned the examples at random to different clusters, and you divide also by this 1 minus the expected RAND index by chance. So while the RAND index is between 0 and 1, because it's an analogous of the accuracy, the adjusted rand index can be negative. If you have a rand index that is below what would be expected by chance, you can actually have a negative adjusted rand index. Now, the adjusted rand index is harder to compute because you need to have these expected values. But in scikit-learn, you have here in the metrics module, you have the adjusted rand score, which is this, the adjusted rand index. So it's easy to compare your clustering to some groups that were already made with the examples. Okay, so what this implies in assignment 2. For the second assignment, you're going to use clustering to cluster images of bacterial cells. So these are images of Staphylococcus aureus. They are taken with fluorescence microscopy. So you have the membrane of the cells is highlighted by fluorescence, and these are photographs with many different bacterial cells, but then they were segmented with an automatic process that includes some mistakes. For example, this is obviously not a good cell here. There are fragments here, but then there are other cells that are really, we can see they are round. So this coccus means the shape of a coconut. They are round cells, and we can see even just by looking where there are some mistakes in the segmentation and where there are good cells here segmented. Now what you have is a data set of 563 images. They all have 50 by 50 pixels. They are in this folder here, and each image has a black background and the segmented region is centered on the image. Now, some images were labeled by the biologists with the phase of the cell cycle. So we have phase 1 here, which is when the cell is not yet dividing. Then phase 2, when the cell starts to divide, and we start seeing this septum forming here. And then phase 3, which is at the end of the cycle, when the cell is about to split into two different cells. So you have this file that has the ID name for each image, and then the label 1, 2, and 3. But most of the cells are actually unlabeled. They have a 0 indicating that no biologist assigned them to any of these classes. So some of the cells are labeled, most of the cells are not labeled. Now, the objective of this assignment is for you to propose some way of clustering these cells in order to help the biologists, for example, select or reject those segmentation errors, select cells of the same type, classify the cells, and so on. And the clustering here may help because if you manage to group similar cells together, instead of having to look at each cell individually to fix these errors or to do these classifications, the biologists can do this with groups of cells. So if they can do, for example, groups of 10 cells or 20 cells at a time, it becomes much faster to do the classification of these cells relative to what it would be if they had to do this one single cell each time. So this is the idea. You need to find some way of helping the biologists. So there is a big difference between assignment 1 and assignment 2. For assignment 1, the work you had to do was mostly following the recipes and doing the implementation and then the validation, testing, and so on. Assignment 2 is a bit more realistic because now you are the data scientists, the biologists don't know about clustering and so on, so you must figure out what you want to do with the data. Part of the assignment is fixed, so you're going to use PCA, t-SNE, and IsoMap to extract 6 features with each of these techniques. Now, this is not a very usual application of t-SNE and IsoMap because these usually are for visualization, but in this assignment, this is only the starting point. You will have 18 features instead of the 250 pixels for each image. And now you must do feature selection or further reduction, whatever you want, in order to optimize the results of your clustering. then you also need to test at least 2 clustering algorithms, k-means and dbScan. Of course, you can test more clustering algorithms. We're going to look at more clustering algorithms, and you can try to improve as much your results, but these two are mandatory. You need to use them, and you need also to fine-tune the parameter epsilon for dbScan by looking at the original paper. So you have to understand what is described in the paper and apply that in your work. You're also going to implement measurements of cluster quality, such as the RAND index to compare with the labeled data that you have, the adjusted RAND index, the silhouette score, and so on, that you can use to try to figure out how good or bad your clusters are and how you can adjust the parameters for your clusters. There's also an optional item there that is only worth 2 points out of 20. But so leave it at the end, do it only if you manage to do everything else, which is to implement bisecting k-means and use bisecting k-means for clustering. But now there are lots of decisions that you have to make. How you select the features that you're going to use, how you optimize the clustering algorithms and select the clustering algorithms, how you evaluate the results, and what recommendation will you give to the biologist. So what would you say your clustering is good for in this context? So that is basically the idea of the second assignment. Think about how to do this unsupervised learning and to extract some knowledge from the data. So practical details, read the assignment page. The assignment is online. Check it occasionally. I may update it if there are some clarifications necessary. Download the data. You have the images. Keep the images in this images folder, because then everything will, the HTML reports and so on will assume that the images are there. You have this file with the labels, and you have these auxiliary functions in this script that can help you generate HTML pages with the clustering of the images, so that you can visualize. It's easier to see how your clustering is working if you generate these reports and then look at the HTML with the images organized according to the different clusters. With your report, you can also use the links to images if you create plots and things like that, and to these HTML reports. So check the instructions on the forms that you have to fill, how you can do that. So these are these TP2 TXT forms with the questions that you must answer. So the next week, the lecture that was planned for Monday will only be for questions, mostly I think about the assignment, because you'll have time to see these pre-recorded lectures until then. The optional exercise is to implement this bisecting k-means. So it's not very hard to implement, but it takes more work than the 2 points it's worth. So leave it at the end and only do it if you want these extra points for additional credit. So to sum up, we saw fuzzy sets, the idea of modeling uncertainty or vagueness in our concepts by using this membership function that is continuous and not just binary. And we saw fuzzy c-means, which is basically similar to k-means but uses fuzzy set for clustering. We also looked at manifold learning, how we can reduce the dimensionality of our data by capturing those hypersurfaces where the data is actually distributed in a way that may be close to Euclidean, so these manifolds. And the RAND index as a way of comparing a clustering to some external indicators of which elements should be together and which should be apart. And this you're going to use in assignment 2. So if you want to see more about manifold learning, you have the documentation on scikit-learn shows you several different methods for manifold learning, more than what we covered here. This is just to give you the basic idea, but you can check that, and it's also a good idea to check the documentation on scikit-learn as you're doing the assignment, because then you can see how you can use these different classes. So remember, next week we will have a session just for questions about this lecture, the assignment, or whatever you want.